Jai Hind. The topic today is classification techniques. In this particular topic, we'll discuss about what is classification, how the classification problem is formulated, what are different applications of classification, and then we will study three methods of classification, that is SVM, support vector machine, Bayesian classification method, and K nearest neighbor, KNN method for classification. So let us start with the problem of classification. Every day if we see all the things, we classify the things. For example, let me say I am crossing the street. So when I am crossing the street, I will decide that currently I should walk or not on the road. That is, it is safe to walk or not when I am crossing the street. When I will decide that it is safe to walk, then we will cross the street. So when we are deciding that it is safe to walk or not, so actually what we are doing the yes or no classification. So what the classification is, the goal of classification is to organize and categorize data into distinct classes. A model is first created based on the previous data, and this model is then used to classify new data. So what we are given some training examples. In those training examples, we will be given the previous data. According to previous data, we'll see that when there is some input, what is the output. So actually in classification, what we have input and output pairs. Classification is supervised learning method. When we are given input and output pairs, those forms our training samples, and based on these training samples, we classify the things. So the training is done based on these input output pairs, which are our training example. And once we once we make our model of classification, then we use that model to classify the new data which is unseen. The classification model is based on training samples and it is used to predict the class of the unseen data. A sample is characterized by a set of features. When we are saying that we are having previous data, so the point is we are given input and output pair. When we are having this input data, we will have some features here. So in this particular example, if I see, I am having X and Y pair, X is input and Y is output. Same way I can have multiple things. For example, if I have to classify something, let me say cats and dogs, two classes I am having, cat class and dogs class. So we will have some features of cat and some feature of dogs. So those features will form our input. Based on those input, we will prepare the previous data in which we will have the two classes information, that is the output, that is cat or dog. Based on that, we will do the classification. So what the classification is, it is finding the best boundary between the classes. Now, where we can apply classification? Classification has a wide range of applications. For example, in personal identification, credit rating, let me say for loan distribution, some medical diagnosis, some diseases there or not, some text categorization, denial of service detection, character recognition, biometrics, image classification. We are having number of applications where classification is used. How do we formulate classification formally? So when we are having the problem of classification, actually what will be given? We will be given an input space R. The input space R, so data is from this R, and we are having some set of classes. Here the classes we have taken as W1, W2 and WC. So what we are having C number of classes. So what is classification problem? The classification problem is finding this function f. This f will map the input space R to one of the classes, R to W, where each x in R is assigned to one class, and this mapping function is called a decision function. This is our classification. Now we'll study one by one methods of classification. So I'm starting with support vector machine. Support vector machine in short is called SVM. It was introduced by Vapnik in 1995. How it works? The SVM maximize the margin around the separating hyperplane. For example, if I say these, I'm having here two classes. This is first class and this is the second class. One class objects have been represented by these small squares and one class is represented with circles. So if we find the boundary in between, there may be different boundaries. That boundary we are calling separating hyperplane. So how SVM works? It maximizes the margin of the separating hyperplane that we will discuss now in further slide. The decision function is fully specified by a subset of training samples which are called support vectors. Solving SVM is a quadratic programming problem. So let us try to understand here. I am having this one class, this is my second class object. So what we have to do, we have to find a good boundary in between. So if I see this, this is one boundary. Okay, so what this boundary is, we decide the boundary which maximizes this margin. Which margin? The margin between the two classes objects. And these touching objects from different classes, these are called support vectors. So now we will discuss this in somewhat detail, support vector machine. So we are starting with a linear classifier to understand the concept. So here we are considering two classes. One is positive class and one is negative class. The positive class we are representing with solid circles and negative class we are representing here with negative circles. So if I consider this particular one, in this I am having a set of objects which I need to classify. Now the question is, how would we classify this data? So we can see here that these are at one side, these objects, and these objects are on other side. So if we consider this one, so what is this? This is a linear classifier. What is linear classifier here? Wx plus b is our boundary and on this boundary this value will be 0. When Wx plus b will be greater than 0, it will denote positive class. When less than 0, it will denote the negative class. So this is one linear classifier. If we see this, it is a good boundary because all the seen positive class objects are on one side and other negative class are on other side. So these are our training samples, training data. Now if I consider this one, it can be represented by this f. This function I have to find. Now what I have to find? I have to find the best function here in SVM. What we talk about maximum margin, that we are trying to understand here. So if I consider this particular one, so what I have to check the sign of this. Sign will tell me it is positive class or it is negative class. This is another option. This is another option, because if we see the previous one, that is also drawing the boundary. If I consider this one, this is somewhat standing. This is also considering one boundary and it is also able to divide the two classes into different sets. It is a separating hyperplane here. Now we can see here that we are having number of separating hyperplanes according to these available samples. What are these training samples? According to these training samples, we are having different linear classifier, different lines, different linear boundaries that segregates positive class object from the negative class object. Now what the point is, which one is the best, which we have to consider. If we consider this particular, that is somewhat standing, which we have seen number of a big number of classifiers here. If I consider this one and I take a negative class, if I take this one, the negative class object has been classified here. Okay, so in this, it is lying near the negative objects, but it is falling according to this boundary in the positive class object. So it can be the case that the negative object can be classified as the positive one. Now see, this misclassified as positive class. Now see, if we would have taken this one, okay, in that case it was correct classification. Now this problem occurs that which I should select. So what we will try to find out here is margin. What is the margin? This is margin. See, this is the classifier. See, this one is the classifier. Okay, this black line, and it is touching this one object of negative class and this one object of positive class. So this is the margin only. This is the margin. Define the margin of a linear classifier as the width that the boundary could be increased by before hitting a data point. So when I increase this boundary, I made it thick, it touched it. It is hitting the positive class, here it is hitting the negative class. So if we see these, so what is there? This is forming the margin. Now if we try to change it, now see, in this particular one, if I consider this linear classifier, I am having a good margin. Okay, this is the maximum margin linear classifier. It is SVM. How SVM works? It finds out the maximum margin linear classifier. It is the linear classifier with maximum margin. So we can see here maximum margin. In comparison to the previous one, we are having a big scope of margin. This is the simplest kind of SVM. We call it linear SVM. This is our linear SVM. These are the support vector. If I check this particular classifier, I am able to go to this much point. It is hitting this particular and this particular. 2 data points from negative class and 1 data point from positive class. So what we try to do, we try to find out a linear classifier which can be increased in width maximum before touching the vectors of the different classes, which we call here support vectors. These are the support vector. These are the data points that margin pushes up against. Now, when we are talking about these SVM, the two types of SVM are there, linear SVM and non-linear SVM. If I consider these data points, we can see that these data points can be divided linearly into 2 parts. Here I am having red objects, here I am having blue object. So this is linear SVM. It is used when the data sets are linearly separable. Linearly separable means we are having data points such that I can draw line between different type of objects. That is my linear. For example, if I consider these as stars and these as circles, so I am able to draw a line in between. Okay, so this is our linear SVM. Now, if we consider this particular example, in this what we are having some red objects, then some blue objects, then again some red objects. Red, blue and red. And when I draw a boundary, I am not able to segregate red objects from blue objects. Here I am having red objects, then in this side I am having red and blue both. If I take this is my, let me say, linear boundary 1. If I take another boundary, that is linear boundary 2. So what I am finding here, I am having on one side on the red object, but on right side red object, but on left side I am having red as well as blue objects. So what does it mean? It means our data set is not linearly separable. So when data set is not linearly separable, what we use? Non-linear SVM. Now the point is, what is the solution to find the maximum margin in nonlinear SVM? The solution is mapping data to a higher dimensional space. For example, if I consider this as the X attribute and we map it to high dimension, that is to X square. So when we are mapping it, so we are getting this resultant. So what is done? mapping data to a higher dimensional space. The dimensions have been increased with help of some power of the existing data. For example, I am having x here. So, we are mapping here x square. We have mapped it to high dimension. Now, what we are getting? We are getting these red objects here and the blue objects on this side. So, I am able to find out a boundary which is separating red from blue. This is the way linear SVM works. So, let us write in somewhat detail. Feature space is mapped to high dimensional. So, let us see this one. This is my x. Here I am having this boundary which is segregating the both but not linear. So, this is non-linear SVM requirement. So, what is the general idea? The original input space can always be mapped to some high dimensional feature space where the training sample will become separable. So, what we do here, we map lower dimension data to high dimension. This is called our kernel mapping. Our kernel may be linear kernels or some Gaussian kernel or some polynomial kernels. So, now what we are doing here, see, we are not able to map, we are not able to linearly segregate it using linear classifier. So, we have mapped it to high dimension. Now, we can see here, now the hyperplane which is segregating these. Now, here we are having blue points, that is blue objects, here we are having red objects. Now, because these were not that was not possible to classify these linearly. So, what we have done, we have used a hyperplane here. We have mapped it to high dimension. Now, we can see here that this plane is dividing these into two different classes. This is one example of non-linear SVM. Few properties of SVM: sparseness of solution when dealing with large data set. If we are having large data set, then our solution is sparse. Only support vectors are used to specify the separating hyperplane. Different objects are not considered for finding the hyperplanes. Support vectors are used to find the separating hyperplane. It is able to handle large feature spaces and it is a deterministic algorithm. We are having a wide range of applications. SVM has been applied to different application domains. For example, text categorization, image classification, biometrics and handwritten character recognition. We have a wide range of SVM applications. So, this is our SVM. Now, one more thing we can discuss here, that is the weakness of SVM. It is sensitive to noise. Noise sensitivity. A relative small number of mislabeled example can dramatically decrease the performance. It is sensitive to noise because what we are doing, we are finding the hyperplane based on the support vector. If by chance the support vectors may be the result of noise, then it may create the hazards here. Now, second thing is, it only considered two classes because we are finding the hyperplane in between the two classes. So, is it possible to do multi-class classification with SVM? Yes, we can do, but we need to do that through programming. With output M, we will learn M SVMs. So, because there is possibility of yes or no, one on both one side, another on the second side. So, to predict the output for a new input, just predict with each SVM. And so, what we have said here, multiple SVMs will be treated. So, when we need to find out the new SVM, we will predict with each SVM and find out which one puts the prediction of on the farthest into the positive region. So, that is the case of SVM, that it is sensitive to noise and it is mainly used for two-class binary classification. Now, the second is our Bayesian classifier. So, now we will discuss Bayesian classification. Bayesian classifier, these are the few important properties of Bayesian classification. Actually, the Bayesian classifier is a statistical classifier. It performs probabilistic prediction that predict class membership probabilities. it will only calculate the membership probabilities because it talks about the probabilistic prediction. It is based on the Bayes theorem. A simple Bayesian classifier has comparable performance with decision tree and even neural network classifiers. It is incremental in nature. Each training example can incrementally increase or decrease the probability that a hypothesis is correct. Prior knowledge can be combined with the observed data. So when we are observing something and we are finding the maximum possibility of the classifier, that is the probability, with help of which we will do the Bayesian classification, that can be increased with help of prior knowledge. So we can use our prior knowledge in terms of prior probability. And a very important point about the Bayesian classification is, although it is computationally intractable, but it provides us the optimal decision making. We get optimal classification result with Bayesian classification method. It is comparable to very good methods like neural networks. So what we have in this, we use Bayesian theorem, Bayes theorem, that is which is used for conditional probability. Let X be a data sample. The data sample that we have, that is called evidence. Now we are not, we do not know the class label. So class label is unknown. Let H be the hypothesis, X belong to class C, because we do not know the label and it is a statistical classifier. So we assume the hypothesis that X belongs to class C. So now the point is, what is the classification here? What is Bayesian classification? Bayesian classification is to determine probability of this hypothesis H when observation is X. When I am having evidence X, then what is the probability of this hypothesis? That is the probability that the hypothesis hold given the observed data sample X. And the prior probability, which I just said, ki this is the experience, this we get from prior knowledge, and prior knowledge comes from the experience. So that is written with help of PH. This is probability of that particular hypothesis. We call it prior probability. This is actually unconditional initial probability. For example, X will buy computer without any condition, regardless of age, regardless of income and all. That is the probability that X will buy computer. What is Px? Px is the probability that the sample X is observed. Now see, this is conditional probability. Probability of X when H is there. It is the probability of observing the sample X. It is the probability of observation. That was the probability of hypothesis H when X was observed. Now we are saying what is the probability of that observation when the hypothesis is actually already there. For example, when we say X will buy computer, given that X is in the age of 30 to 40 and is having medium income. So what we are having here, we have given this the probability with few conditions. So something is already there, and what are those? Hypotheses. So Pxh is the probability of observing the sample X given that the hypothesis holds. This is Bayes theorem. Probability of H when X is there is equal to probability of X when H is there, means the hypothesis hold, into probability of the hypothesis, which is the prior probability, and Px is the probability of observation. So we can say that the posterior probability is equal to likelihood into prior divided by evidence. This is our posterior probability, this is our likelihood, this is the prior probability, and this is the evidence. What we are predicting? We need to predict X belongs to Ci if and only if the probability of Ci when X is observed is the highest among all the probabilities of different classes when the observation is X for all the classes. So we will find out probability corresponding to all the classes when observation is X, and we will take that which is having the highest among all. So this is the way the Bayesian learning is used in Bayesian classification. And what is there? We require initial knowledge of many probabilities, so it is having the significant computational cost. So now let us discuss with a formal method, formal representation of the Bayesian theorem, Bayes theorem. So let D be the training set of tuples and their associated class labels. It means we are given the training samples, input and output pairs, and each tuple is represented by ND attribute vector. So let me take the input is x1, x2 up to xn. This is my input and this is my output. So input I am representing with the attributes x1, x2 and xn. And now I am considering that I am having here m classes. So my classes are C1, C2, Cm. Classification is to derive the maximum posterior, that is maximal probability of Ci when X is observed. So this can be derived from the Bayes theorem. What Bayes theorem says? Probability of ith class when X is observed is equal to probability of observation when class is Ci into the prior probability of Ci divided by the probability of evidence, that is Px. Now, since Px is constant for all classes, so we can exclude it when we are making the calculation. So actually what we need to do, we need to find this value, that is the numerator here. And what we need the maximum numerator, because every numerator will be divided by the same evidence probability. So that is not required, this division is not required. And what we will take the numerator. Now see, the probability of observation when class is there is actually weighted with the prior probability of that particular class. So this is the prior probability of this particular class for which we are finding the likelihood. Now we'll talk about a variation of Bayesian classifier, that is Naïve Bayes classifier, because if we see here this, when we are saying that probability of X, now I am having X as this collection, because I am having X attribute which is having x1, x2, X input which is having x1, x2 up to xn attributes. So if I take this simple assumption that all the attributes are conditionally independent, it means no dependence relation is between the attributes. So we can simplify our method, it will reduce the computation cost. Now what is the what we have said, that all are conditionally independent. It means probability of x1 when class is Ci is independent of x2, and when x probability of x2 we are calculating, we are finding that it is independent of all x1, x2, x1, x3 and so on. So what we are assuming, that some ith attribute is independent of all other n minus 1 attributes. So it reduces the calculation. It is Naïve Bayes classifier is very popular and it has shown a very good performance. Now the last one is k nearest neighbor. This is another classification method. In this classification method, what we do not among the various methods of supervised statistical pattern recognition, the nearest neighbor rule achieves consistently higher performance without prior assumptions. In this, we will not have any prior assumption about the distributions from which the training examples are drawn. Training set involves again both positive and negative cases. What does it mean? It means, let me consider two classes, and I am considering one as the positive class and one as the negative class. So the training set will consider both negative and positive class cases. Now a new sample is classified based on these data samples, which is our training set. So if we consider this training set and we are given a new sample, So a new sample is classified by calculating the distance to the nearest training case. So we will calculate distance from all other cases, and what we will find, it is classified by calculating the distance to the nearest training case. The sign of that point then determines the classification of the sample. So we will find out the nearest one and we will classify according to that nearest one. This is k nearest neighbor method. The KNN classifier extend this idea of neighbors by taking the k nearest point. So just we said on the last slide that it talks about the nearest neighboring case, training case. So what we do in k nearest neighbors, we take actually the k nearest points. The KNN classifier extend this idea by taking the k nearest point and assigning the sign of the majority. What does it mean? It means we will take some values k which are in neighborhood and we will check signs of all. Let me say m are positive and n are negative. If m are positive and n are negative and m is greater than n, then that particular new point, new sample will be assigned to the positive class. If m is less than n, the number of positive points is less than the number of negative points, then the new sample will be assigned to the negative class. So what is the common values to take k? It is common to select k small values and odd. Why do we take odd values? Because if we are having some even values, let me say 2, and I am having a point, a new sample which is having in its neighborhood 2 values, one is positive, one is negative, then tie will come. So to break these ties, what we take, we prefer to take the odd values of k. Larger k values help reduce the effect of noisy points because there may be noise and one may get wrongly classified because of noise. So what is the solution to that? We can take a larger k values that help reduce the effect of noisy points within the training data set, and the choice of k is performed through cross validation. We use the cross validation method to find a good value of k, the choice of k. So how it works? We take all the instances, all instances correspond to points in the ND space. So let me take these points. If I consider this ND space, n-dimensional space, and I am having all the points, and here what are my points? I am having 1, 2, 3 positive class point and 1, 2, 3, 4, 5. Sorry, we are having 4 positive class points and 5 negative class point. Now what my new sample is, that is XQ. We represent it as a query point. So if we take 5 neighbors, if we take the k as 5 and we see the 5 neighbors of these, what are the 5 neighbors of this query point? 1, 2, 3, 4 and 5. All instances correspond to points in the ND space. The nearest neighbor are defined in terms of Euclidean distance. We will find out Euclidean distance between 2 points. So by finding the Euclidean distance and then selecting the minimum 5 distant points, we got these 5. Target function could be discrete or real valued. For discrete valued, KNN returns the most common value among the k training example. What it returns? The most common value. So if we consider this, in this there are 5 neighbors and 2 are positive and 3 are negative. So which is the common value? That is negative. So XQ will be assigned to the negative class. So it depends on that what are the neighbors and how these are assigned, to which class these are assigned. Based on that number, it will be assigned to the neighbor class, which is to the class of all those neighbors which are more in number, most common value. Now, a few points about KNN. When KNN is used for real valued prediction of unknown tuple, then it returns the mean value of the k nearest neighbor. Discrete we have seen here, there. In case of discrete, what it returns? In case of discrete valued prediction, it returns the most common value class. In real valued, it take all the neighbors and it returns the mean value of the neighbors. Now, there is one more concept related to this that we can apply. If we consider this particular example, in this I am having this query point, and these are the two positive neighbors, and these are 3 negative neighbors, and we take the 5 neighbors. So, what we will get? These. But what is most common here? The most common is negative. If I see this, I should assign this query point to negative class. But from this Euclidean distance, from this diagram as well as by calculating the Euclidean distance, we are able to see that it is very likely to the positive ones and it is far away from negative. Comparatively, a good distance is there. So, according to this view, it seems that XQ is positive. But when we are taking 5 neighbors, it seems to be that it should be negative. So, we can have the weighted concept here. So, that we call distance weighted nearest neighbor algorithm. So, KNN can be given weights. We weight the contribution of each of the k neighbors according to their distance to the query. It means its contribution will be more and its contribution should be less. That's why we assign the weights, and weights are inversely proportional to the distance. If distance will be high, the weight will be low. If the distance will be low, weight will be high. So, we can see here for these more weight will be given to these 2 positives and less weight will be given to these 3 negatives. Although we have considered all the 5 objects in the neighborhood, but more weight is given to the nearest points and less weight is given to the other points. KNN is robust to noisy data by averaging k means by averaging k nearest neighbors. So, this is KNN. So, in this particular lecture, we talked about the classification problem, introduction to classification. Then we discussed 3 methods, that is SVM, KNN, and one for statistical classification, that is Bayesian classification. Thank you. Jai Hind.